Now that we understand what a scatter plot is and what a correlation is, let's talk about the process we use to get there, the linear regression. So a regression equation has this form. Now, if you remember from college algebra, the form of a line was y, or the slope-intercept form of a line was y equals mx plus b. Well, here the m is in that b1 spot and the b is in the b0 spot. So the y is the predicted variable, the response variable from the regression, and the x is the predictor variable, the explanatory variable from the regression. The b1 here is the slope. The slope is related to the correlation coefficient, okay? And the b0 is the y-intercept of the line that we've drawn through the points, the line of best fit, which we're going to describe in just a moment. And this y-intercept may not always make sense for the context of our problem. It depends on where our data is. Like in the previous example, we looked at years since 1900. So if I have a y-intercept that's at -47, that's back in the 1800s, that might not make sense for the context of my problem, okay? Now, our intercept is always in units of y, okay? Now, some guidelines for using the regression equation. You want to be careful with extrapolation. Let me go back just a moment. This equation is good over the set of data that we use to form it. Extrapolation is predicting values outside of that range of observed data. Just like I gave the example a minute ago of, our percent of respondents in the 1900s might not make sense if we're extrapolating back to the 1800s. So you always want to be very careful to realize that the regression equation is good over the set of data, and we can use it to predict beyond the data a little bit, but those predictions may not always be accurate. So we want to be careful with that extrapolation process. So a residual is the difference between our observed value and the predicted value. To actually calculate the residual, we take the observed value and subtract what the predicted value is. How do we get the predicted value? Well, we plug in, whoops, wrong way, we plug in that x to our regression equation. So whatever our value of the variable is there, we plug in as x into the equation. That gives us the predicted value, and the observed value is the actual y component of the data value that was plotted on the scatter plot. A negative residual means the predicted value is too big. So if I subtract the predicted value from the actual value and it's negative, then my prediction was too big, like for example, here. And then a positive residual means the predicted value is too small. Like if I look at this point right here, whoops, go back. This point right here, if I subtract the residual, if I subtract the predicted value here, then the residual would be positive because my predicted value was an underestimate to what the actual data point is. Whereas over here it's negative, okay? That's the difference. So this length here is representing the length of the residual. So some of my residuals will be positive and some negative. In fact, about half of them is going to be positive and half is going to be negative. So if we just summed up all of those residuals, we'd get back to 0 because they had positives and negatives would cancel each other out. So instead, what we do is we take those residual values and we square them. Because remember, if you square anything, it makes it positive. A negative times a negative is a positive. And so if we then add up the squares of all those residuals, the smallest possible sum there is our least squares regression line, okay? So that's our line of best fit for the data. The least squares regression line is the one that minimizes all of the residuals and gives us the minimum value for that regression line, the minimum value for the error in prediction in that regression.